Sid Choudhury, and I'm the VP of Product here at Yugabyte. What we're going to talk about today is essentially about how do we scale transactional applications across multiple regions, and that too with low latency. Here is a quick agenda for the talk. We're going to first talk about a little bit about us, and then we'll dive into the state of the art about scaling transactional applications, especially in globally distributed user populations. And then we'll introduce Yugabyte DB as a solution for that problem. We'll have a live demo, and then we'll spend a good amount of time in question and answers. But feel free to keep asking questions in the questions window, and we'll get to those at the end of the talk. Okay, let's get going. So first, a little bit about us. We are a company, little bit over two-year-old company, founded by a team of ex-Facebook engineers who were responsible for taking Facebook's data platform from its very infancy to all the way till a mission-critical data platform running multiple applications. All of that ran on Apache HBase, and the team was also very much involved in Cassandra before it was called Cassandra in its early days. We have tried to essentially recreate the same team here at Yugabyte with engineers from Facebook, Oracle, Nutanix, and so on. So now let's talk about scaling transactional applications with geo-distributed users. So first is if it's a geo-distributed set of users, that means your users are actually trying to access your web or mobile application from multiple regions around the globe. For the sake of simplicity, I've picked 2 regions. And let's say you have done actually the hard work of containerizing your application, and even breaking down your application into microservices, containerizing them, using orchestration tools like Kubernetes to actually do these deployments into any cloud of your choice. But the question that always vexes application developers is what to do about my data, and especially about transactional data, which is like very, very business critical. My user records, my customer records, the invoices that are attached to those customers' records, the products those customers are viewing, these are all transactional data elements. So the most common deployment pattern is that of a relational database. And here I'm showing you Postgres. It can very well be MySQL, it can be Oracle or DB2 and so on. And usually since these databases have the sort of monolithic characteristics, a single instance of that database is deployed in a single region, even though your application microservices are deployed across multiple regions. And now your reads and writes are coming in from those microservices into that that SQL master. The region 1, which is located in the same region as the database, experiences low write latency, low read latency, everything is great. But any other region that is farther away now has to pay the sort of penalty of having the network traffic traverse over potentially public internet to come and talk to the database. So other regions experience higher latency. Now that's not an HA setup. You cannot handle failures, and you cannot if you want to serve reads, more reads, then what customers typically do is they deploy another instance of let's say Postgres and call it the slave instance, and then use more commonly use async replication. Sometimes it's hourly, sometimes it's nightly, to start powering that instance. It's a completely different instance of the database. So that they can not only serve more reads, but also if let's say the node on where this SQL master was running that dies, you can manually promote the SQL slave to become the current master. Now, there are challenges in this kind of deployment. The two ones I've touched on are is users in any other region, including here in this case region 2, will experience high page load times because now the database is farther away. And also there is no horizontal write scaling. Now if you need your database now needs to accept more writes, then you cannot just add a new node into the system and that node will start serving writes. You have to what is known as vertically scale, which is make your underlying nodes, compute, storage, everything more powerful by moving potentially the database to a newer machine altogether. So this is the most common deployment pattern. Now let's say you want to start solving one of those problems, and that is, how do I scale my writes? And the most common write scaling approach is that of sharding. What you do is treat the original instance as one shard of the overall application's data needs, and shard is like a partition of the overall data, and you deploy another master for your other shards. So in this case, I have shown two shards. So there is sort of two master, one master, one slave for shard one master, one slave for shard 2, and they both are going through the same async replication approach. While we have certainly sort of increased the ability to take on writes, we have actually made it very complex for the application to deal with this scenario, because now the app code has suddenly become aware of where each shard is located. And every time I have to add new shards as I'm experiencing more growth, or I'm removing shards because I don't need that much capacity anymore, app code has to change. Not only that, in the background, your operations team is also very busy, because every time you add shards or remove shards, they own the problem of manually doing data migration and rebalancing across all the instances that are now available. So yes, we tried to solve write scaling, but we introduced a new set of problems. Let's say we now want to solve the other problem that we had experienced in the original master-slave architecture, and that was of high latency for our non-region 1 users. And the way to do that is now make the database come closer to each region where your apps are running. And what most common approach is actually just create multi-master deployments where each region has a full copy of the database running with a master and a slave configuration, and users are writing to that database as if it were the complete database. Now the challenge is the same record now can be written in sort of both instances. Let's say I sent an order to an e-commerce application while I was on region 1. I took the flight overnight and I went over to the other part of the country, and now I don't want my order and I want to cancel it. Both the initial order went into master 1 and the cancellation went to master 2, and now we're not clear actually which is the source of the truth, because the conflict between these two transactions will be resolved in a non-deterministic manner after both the transactions have committed. And this is without even bringing sharding into picture, just pure multi-master RDBMS architecture. The big challenge here is that in order to solve my users' latency concerns, I have now introduced data inconsistency in my data architecture. Again, the complexity is handed back over to application developers who have to do compensating logic in the code to handle this inconsistency. So as I am trying to solve my challenges of scaling and high availability, and also satisfying users with low latency needs, all of a sudden I am presented with a sort of a whack-a-mole set of challenges, and I both, sometimes it's onerous on the dev team, sometimes it's onerous on the ops team, and this sort of is what the state of the art in transactional database infrastructure looks like today. Now, some advanced enterprises actually say, okay, I'm not gonna touch the sharding, multi-master. All these configurations are very complex when it comes to RDBMSs. I'm gonna adopt actually a more modern architecture. I'll bring in NoSQL for data distribution, and I'll bring in a cache layer to actually bring in data from multiple databases, and now use that as my primary serving cache. So what they do is they introduce a NoSQL database like Cassandra, which is good at distributing data across multiple regions, and also they bring in a caching layer like Redis into the equation. So I can now sort of see how my data will move. The moment I write my data into my SQL master, I am also writing some amount of data in my NoSQL database, which is Cassandra. And if SQL master is actually sharded, then my app was already aware of that information. My app now also needs to be aware of what data is actually being distributed by the NoSQL solution. Is that also present in the SQL master, or is it net new data that is being written? So these kinds of data silos are now very much in the minds of the dev team as they are coding. And now with the cache being in the equation, I also have to understand cache consistency issues. Yes, I do get some latency, low latency reads in return, but now every access has to be made consistent with the data in the underlying persistent data stores. Again, more challenges for the dev team. Coming to the ops side, they are not faring well in this equation as well. Now they have 3 independent database infrastructures, each having its own replication semantics, its own failure models, its own backup, restore, monitoring. The whole problem for operations teams becomes actually 3x more complex than what they had originally started out with. So net result is that it's a fragile infrastructure with data consistency issues. Every time there is an outage or an issue that is brought forward, you are now doing metrics, logs, analysis across multiple different databases. Overall, this essentially means loss in agility in delivering software for business. The common question that's asked is, yes, this looks complex, but public clouds like AWS have given these managed services. Do they make my life actually easier? Let's see. What does AWS provide, right? Redis. Amazon has a managed Redis service called Elastic Cache. For my SQL solutions, Amazon has a managed service in terms of Aurora or RDS. And for a Cassandra-like, high write throughput data distribution use cases, Amazon has DynamoDB. So Amazon has exactly those same 3 layers now available to you in a managed form factor, but architecturally, from a development and operation standpoint, it's still complex. It's actually the same siloed architecture that you had previously used in your non-managed services world. So it actually doesn't help a lot. So the big question that we want everybody to think of is, it's 2018. Like, there has to be a simpler approach than what we have been doing for 20 plus years. And that's where we come in. We actually believe that we are that simpler approach. So let's take it one by one. We are Yugabyte DB is a new transactional high performance planet scale database, and we have these sort of 5 pillars that we consider as the foundation of our database. So let's take one by one. First is the transactional aspect, which is paramount for storing OLTP mission critical data. So at the core of the database is our storage engine, which is essentially a document based, strongly consistent storage engine. So you can think of it as a transactional key to document store. Given a key, you can really easily and consistently access documents inside the storage engine. And it's built on top of a very heavily customized version of RocksDB, as well as the replication is handled through a distributed consensus protocol known as Raft, which has been proven in real world applications to be one of the more I would say resilient and easily understandable consensus protocols. For example, etcd in that stores Kubernetes metadata also is based on Raft. On top of this transactional key to document storage engine, we have built the notion of distributed ACID transactions. Now, ACID transactions, which inherently mean that I can take a bunch of database operations, put them inside a begin transaction and end transaction, and all those operations will happen or not happen as a coherent unit, is something that is foundational when it comes to mission critical data. In monolithic SQL databases, you take them for granted, but the moment you come to the distributed scale out world, you cannot take them for granted, because those databases which primarily are NoSQL, they actually forsake the ability to have ACID transactions in the promise of giving you some higher performance in return. What we have tried to do is bring in the concept of distributed ACID transactions into the picture, while also ensuring a very high degree of performance. So let's tackle that now. Performance comes in two form factors. One is ability to do low latency reads, because for user facing applications, reads probably outnumber in volume than writes. And since it's mission critical data, you want to actually make sure the writes are strongly consistent, they're replicated out before they are committed, but my reads are extremely fast. And that's where we provide a tunable knob for you to choose what kind of consistency would you like to have from a read standpoint. If you want absolutely strong consistency in reads, then it is a slightly higher latency. If you can tolerate slightly lower consistency but still remain timeline consistent, which is your ordering of data is still maintained, then you can get an extremely low latency read. Secondly, it's about throughput. We've designed the database to be able to handle very high write and read throughput by ensuring that the LSM based storage engine is able to work on large amounts, is able to process large amounts of data and also store large amounts of data with high density. Third aspect is planet scale, and this is where the ability to distribute data across the globe in a consistent manner kicks in. And this is where we'll actually spend most of the time in the remaining part of this talk, talking about how to distribute data across that. But in one of the, I would argue, one of the foundational aspects of getting there is having the ability to do auto sharding and auto rebalancing of your entire data as new nodes are added or existing nodes are removed. Otherwise, if sharding is handled by the application code and rebalancing is handled by operations team, then you will not achieve global data distribution. It's almost next to impossible of getting there. Cloud native, it's sort of becoming a buzzword, but there is some concrete meat behind it in the form of today's data infrastructure, or for the matter any mission critical infrastructure, has to be able to be sort of purpose built for the container era, where you get sort of extreme amounts of portability from one kinds of hardware to another kind, one kind of cloud infrastructure, one cloud platform to another, running in on-premises today, moving to the cloud tomorrow. All those are like the promise of containers, but containers are inherently stateless in nature. So you need, in order to run database inside containers, you need a database that understands the container's need for agility and has a sharding, replication, rebalancing mechanism that works against that containerized world. Another question that's sort of typically asked of us is, since you're strongly consistent, that means you are not fault tolerant. That's actually not true. The famous CAP theorem says that in the presence of failures, you have to choose between consistency and availability. So in the presence of failures, we choose consistency because we call ourselves a consistent and partition tolerant database, which is CP. However, through uh, our ability to heal by electing a new leader for every shard that's present in the database, we're able to reduce the availability to just a matter of couple of seconds. So you in a way you can have your cake and eat it too. I mean, that's how today's modern database infrastructure looks like. In fact, Google Cloud Spanner from Google and Microsoft's Azure Cosmos DB have a very similar architecture around how they handle consistency and fault tolerance. Last but not the least is the nature of building open source software and building an ecosystem around it. So our core of our database is actually Apache 2.0, so that enterprises and startups can actually adopt the database and the full database without worrying about sort of complex legal ramifications and so on. And we explicitly chose not a GPL or AGPL license for that purpose. Secondly, not only the core is open, even our APIs or the language that you use to actually talk to the databases are also open. We do not have our own proprietary language. In order for you to work with, we have extended existing open source languages. Today we support Apache, Cassandra, and Redis. And our OneDotO version, which is releasing pretty soon, will have PostgreSQL as the third API flavor for us to support. So that's in a nutshell what Yugabyte DB is. Now let's take a little bit deeper look into the architecture. I'll start with the API layer. So we have these three APIs: Cassandra compatible, Redis compatible, and PostgreSQL. We have extended them, and we'll talk a little bit about the key extensions in each one of them. But for each of those APIs, we have automated sharding and load balancing. So that as you create more tables, you add more data into Redis and so on, each element is automatically getting partitioned out into its own what we call as tablets. And those tablets have leaders, which is where writes are taken, and tablets has followers, which is where we ensure that there are enough copies of them so that if the leader dies, we can re-elect a new leader automatically in just 2 seconds. And this basic replication is based on Raft, but on top of that, in order to support globally distributed transactions, we have a transaction manager running in each of our data nodes, and that does tracking of where each of the keys need to be updated. It does provisional data management, does clock skew tracking, and ensures that your begin transaction, end transaction, every operation inside that becomes ACID. You can run this database on top of any cloud, and we'll see demos in that, and we're deeply integrated into each of the clouds. And also at the top layer, since we chose an open ecosystem approach, we are able to benefit from the multi years of effort that has grown into growing each of these ecosystems. So you're able to build Spring Boot applications and plug them into Yugabyte. You're able to run as us as a more resilient, more dense Cassandra in the SMAC architecture, which is Spark, Kafka, Spark, Mesos, Akka, Cassandra, and Kafka. And also you can run frameworks like Janus Graph, which is a graph database framework, and Kairos DB, which is a time series database framework. So the open ecosystem has got lots of power for getting started and building applications fast. So now let's dive into each of the APIs a little bit more. Why SQL is the first API? It's Cassandra compatible, stands for Yugabyte Cloud Query Language. So it essentially gives us an ability to have a transactional NoSQL database that has both support for single row and distributed ACID transactions, is able to do low latency reads and sort of high throughput reads. The extensions that we have made are not just in the ACID world. We have also made secondary indexes to be consistent and performant. We've added a native JSON data type to make sure that you can even run Mongo type workload patterns. Cassandra does not have a native JSON data type yet. So that net result is that you get relational database like data safety with NoSQL type agility and performance. Redis is our Redis compatible API. It stands for Yugabyte Dictionary Service. So now you can use us as a distributed transactional key value store. So that any applications that can benefit from a key value modeling can just plug in very easily. Since Redis on its own right does not support linear read and write scaling, we are a very important value add into that equation. Having auto sharding, auto rebalancing, fault tolerance, all this essentially allows you to adopt a Redis-like API without worrying about the scale out and availability semantics that are extremely I would say brittle in the basic Redis server. Also, we have made enhancements to the API in the form of a native time series data type. Last but not the least is the PostgreSQL API. We're wire protocol compatible with PostgreSQL. So now PostgreSQL, as you know, is a monolithic relational database. So if you want, the big problem is about write scaling, as we looked at, and now using our PostgreSQL API, you essentially get a distributed PostgreSQL right at your fingertips. You get the same benefits of scaling, auto sharding, fault tolerance, and so on. And we're working slowly towards having joins implemented in a performant manner, so that you don't have to essentially make even that compromise. Some of the linear scalability testing we have tested up to 50 node clusters, 25 nodes, as you can see, has 1.3 million reads and 500,000 writes. And then as you add more nodes, gradually the load increase, the throughput rate actually increases linearly. Right? That's what you want in a scale out database. Multi-region availability and scalability is, like as I pointed out, is foundational. So this is a screenshot from our enterprise edition, which we'll use in the demo. You can actually deploy clusters all around. You can deploy a single cluster that stretches all around the globe if that is the level of consistency that you need. But there are a lot more additional options that you can do to make sure that you even have a lower write latency while having extremely low read latency. And we'll touch on many of those things as we move forward. So one key way of doing this this low latency approach is having something called as read replicas. Now, read replicas are a lot more common in the relational database space than they are in the NoSQL database space, because in NoSQL, every replica can function as both reader and writer, but there are no consistency guarantees. Whereas in SQL databases, your read replicas are for only serving reads, and they are timeline consistent. They are slightly stale compared to your master copies. So very similar approach to NoSQL SQL databases that we have used here, where your primary cluster is in region 1 on, let's say, cloud 1. It can be on premises, and you're using async replication to create a new cluster, a read replica cluster in region 2, and that can be in Amazon. And so that as as your and you do that, let's say to scale read volume during high peak traffic, let's say Black Friday. So what you as application clients are trying to, let's say, read a key in tablet 1, then the tablet 1 will have a leader and a follower, obviously, in the primary cluster, but it will also have an observer in the read replica cluster. So now your application has a choice on a per call basis as to which read you want to take. You can do your local region read, and if, let's say, that region happens to be the read replica cluster region, then you will get a very fast read. Let's say it's a different app client where this read replica cluster is not the local one, and you just want lots of read throughput, then you can enable follower reads so that you can even read from the follower copies. And last but not the least, if you need absolutely correct information, the latest write is what you want to serve back as a read, then you get to go and talk to the tablet 1 leader, right? And there is an increasing latency aspect built into this approach, where the strongest read is the most consistent, and it can be farthest away, hence will have a higher read latency. Multicloud is foundational to today's database infrastructure and to all kinds of infrastructure, I would argue. So we support all the major clouds, and we understand deeply how each of the clouds has a notion of regions, availability zones, instance types, storage volumes that are mounted to those instance types, the VPC architecture that allows you to put a nice security perimeter for your mission critical data, so that you can just develop and operate your applications with a peace of mind. So now let's take a look at a real world case study and see how all the things that we have talked about are actually coming to life. So imagine, go to webinar, the service that you are using. Imagine what its user identity service looks like. As you can think, right? That service will actually need to serve users all across the globe. This webinar is probably being attended by folks from India, from Japan, from Europe, and so on. So as those users log in, as they change their passwords, as they view their profile and meeting details, all of these experiences need to be low latency. However, the challenge is that if it's a single database cluster and it is mastered in one region, then you cannot have that kind of a low latency experience. So what is the most common deployment pattern today for solving this use case? So first and foremost is a MySQL master slave replication architecture. It can be even Postgres. Then, as we saw, bringing in a NoSQL like Cassandra to actually do the data distribution into multiple different regions. And since each region needs very low latency read access, you also augment with something like a Couchbase, right? So we saw a variation of that in the example before, which was Postgres, Cassandra, and Redis. You can very well imagine the same is true with this MySQL, Cassandra, and Couchbase style deployment. So that your writes are only taken at the MySQL master, but then they slowly get distributed out, and your let's say password information also gets distributed out. It gets cached inside this Couchbase instances, and let's say if you do a change password, then there is an invalidation request sent out all the way back to those Couchbase instances. So the next time user tries to log in, that login has to go fetch the latest password information, most likely from the MySQL master. Very complicated architecture, very fragile, lots of maintenance headache. How does a Yugabyte DB like solution solve this problem, right? So let's take the workload that needs the strongest consistency semantics, and that is login and change password. That is just in Yugabyte's speak, it's just a single cluster with nodes across the globe, right? It's the primary data that is stretched all across the globe. So in this what you get is global write consistency, but your writes now have to travel over wide area networks, so write latencies will be lower, will be higher. Low read latency because you have turned on local region reads, as we saw. So your reads are extremely fast. Every user, if I'm a user in the US and I'm traveling to Europe, my follower data is probably already there by the time I get there, and I'm able to read from my followers right then and there without coming back to read from my leader data, which is stored in, let's say, US. And this is one of the most resilient architectures, because it can survive, if you have a three node deployment, then you can survive any region outage with zero downtime and zero data loss. Both of them are true in this world, because the remaining two copies of the data, however far apart they may be, they will ensure that your application continues to be served and no data gets lost. Workload type 2. Now let's talk about a different workload where I'm just trying to read information that sort of rarely changes, my profile information, the meeting that was previously scheduled, right? So in that case, it's a different architecture. What you want to do is have your data actually the primary cluster inside probably a single region, but have multi AZ, so that you get AZ downtime, resilience over AZ failures. But then you use a lot of read replica clusters to spread your data out into different geographies. And that also you can have different replication factors around those read replicas. Let's say you want more read throughput in the Asia Pac region, so it can be a replication factor 3 with 3 nodes, or and in Europe and South America, you can just replication single node with replication factor 3. So the benefit here is that the write latency when I'm adding new meetings and so on, when I'm changing my profile, it has a very low write latency and high write throughput, right? And because I'm not actually traversing region boundaries in order to make that happen, I still have to pay the cost of traversing network if let's say a Japanese user is trying to change his password, but that's okay. But that's okay because these operations are very rare. Creation of meeting is much more rarer compared to joining a meeting, right? So now comes the low read latency aspect, which is the joining a meeting, looking at my profile and so on. That you will now be able to serve without coming to the primary cluster. You can just serve from your read replicas. Now, in this scenario, since my primary cluster inside a single region, I won't be able to tolerate that region's failure, right? But any AZ failure, which is like power domain kind of failures or rack failures that happen inside that single region, I can tolerate with zero downtime and zero data loss. So this and what we typically see is that a GoToMeeting like infrastructure will use both combinations of clusters, workload type 1 and workload type 2. Okay. There is an alternate deployment for workload type 2 when for some reason, let's say you well, there are two reasons. You can increase data resilience by actually using multiple cloud providers inside a single geographic area, or if one cloud provider is actually not giving you doesn't have availability of multiple AZs in a given region, then you can augment it by bringing in other cloud providers. So here is, I've just taken that primary region. Now I have made it run on 3 different clouds: one AZ in on-premises, one AZ in Amazon, and one AZ in Google. So this is, they're all geographically very close to each other, but they're still more resilient compared to running all of the 3 in let's say on-premises. Okay, so a variance of that. Now what I want to do is hand the webinar over to Karthik Ranganathan, who is our co-founder and CTO, and he will walk us through these scenarios of the real-world case study that we just saw in slide form, in actually live in our enterprise edition of our product. Karthik, over to you.
Thanks, Sid. Okay, guys, so I'm going to show the 3 scenarios that Sid talked about really quickly. And just to recollect these, the first one is a completely globally distributed and consistent setup. The equivalent of that here in our enterprise edition, like first off, our enterprise edition is configured to run with Amazon, Google, and an on-premise data center. So if you go look at the cross DC user identity 2 universe, this is running in the exact same setup as what Sid talked about in the slides. We have 2 copies of the data running in US West, 2 copies in US East, and 1 copy in Tokyo. Okay, all of this is running on the Amazon cloud. It's running across, therefore, 3 regions, 3 availability zones, and 5 nodes in this setup. Now, it can use both the Cassandra YSQL API and the Redis Redis API. So both of them can be used, but this example is really writing data into the Cassandra user ID table. Now, if you go look at the workload and its characteristics, what we expected is that we expect a low read latency because all of the apps are reading data from their local data center or their local region, and we should expect it to survive outage, but be globally consistent on writes. Now, we have about 2,000 reads and about 50 writes happening on this cluster. What we find is that the write latency is around 191 milliseconds, and this is because it writes data globally for consistency, whereas the read latency from doing a read from the nearest data center is just 260 microseconds, right? So it's really, really fast reads, but globally consistent writes. Now, let's go take a look at the deployment type 2, the workload type 2, where you actually want low write latency and low read latency, right? But of course, there's going to be some lag in the replication of data. So here's an example of a setup that's running a 3-way replicated cluster in a Google Cloud for the primary data, and another 3-way replicated cluster in Amazon for the replica. This is very similar to this setup. There's 1 3-way replicated primary region, and there's 1 remote region that's running US West, US East, respectively. So if we go look at the performance of this system, and once again, going back to the slides, we expect low read latency and low write latency as well, right? So what we find is this system is doing about 40,000 reads and about 1,000 writes concurrently. And what we find is that the write latency is just a millisecond and the read latency is 0.2 milliseconds, about like 220 microseconds. So what we find is it is indeed really, really fast on the reads and the writes. In this setup, what's happening is the writes are all flowing through the primary region and the reads are happening both in the primary as well as the remote read replica region, right? So, and we'll be able to go verify that with the set of nodes. Some of the nodes, which are the read replicas, will be performing only reads, whereas other nodes, which are like the primary nodes, will be performing both reads as well as writes, both with low latency. Okay, finally, let's go take a look at the third workload type, where you have the data in the same region, but in availability zones across different clouds. So here's an example of that. In this example, we've got data spread across Amazon and Google. It's set up as an on-premise data center, which has 3 availability zones, 2 in Amazon and 1 in Google. And the nodes get automatically distributed across Google and Amazon, right? And then this system works really well in places where you want to really protect yourself against failures of any one cloud provider. That's all I had. Handing it back to Sid.
Okay, so let's get back in. Want to point out that Yugabyte DB is actually something that you can try in just minutes on your laptop. We support various ways of deploying the binaries for macOS, CentOS, Ubuntu. are available. Also, you can use just regular Docker from on your laptop, or even Minikube, which is Kubernetes' local deployment. You can use that to get going. Right. That's it. We have reached the end of the presentation. We'll take some questions at this time.
Hey folks, so for questions, please type in your questions into the questions box. We already have a good bunch of questions, Sid, so I'll get started with that, but please keep them coming. Sid will keep answering them as you guys type it in. So first question, Sid, how do you differ from Azure's Cosmos DB and Google Spanner?
Excellent question. So let's start with one by one. Google Cloud Spanner is Google's SQL, a relational database that can scale over multiple regions. It is actually where we love its underlying architecture around using Paxos, which is where the origins of Raft come from, to actually handle data with very strong consistency, high and with even really high availability. Part of it, high availability, comes from using something called as a true time, which is Google's own proprietary atomic clock. And they have factored the cost of infrastructure into actually the pricing of Google Cloud Spanner. Right. We are similar to Google Cloud Spanner in the form that our underlying storage and replication architecture are actually very similar to that of Google Cloud Spanner. However, we don't like the performance characteristics of Google Cloud Spanner. It actually is not a good value prop for slightly ever-growing data. Let's say if you want to store users' sort of reviews alongside the product catalog, then that reviews is slightly ever-growing data, whereas product catalog is much more bounded data. You will actually have to use a separate database in order to store the review information. Also, the performance semantics of not knowing exactly where the leaders for various shards are, given the limitations of SQL as a language, also hurt in doing low latency transactions. Secondly, coming to Azure Cosmos DB, we actually like Azure Cosmos DB's approach of using multiple different APIs on top of a single storage and replication architecture, very similar to our approach of using Apache Cassandra, Redis, and PostgreSQL. However, Cosmos DB does not support distributed asset transactions. So as a result, you can store your user reviews in there, but you will not be able to do your product information, because when a user buys something, you will need to decrement the inventory and increment the shipping of the item to that user at that time, and that kind of a sort of a distributed asset transaction is not possible in Cosmos. So in a way, the API layer is inspired by Cosmos DB. The storage and replication architecture is inspired by Google Cloud Spanner.
Great. So here's a quicker question, probably, Sid. Question is Yugabyte a query layer that uses multiple databases like Cassandra, Redis, and Postgres underneath?
Oh, yeah, this is a common question we hear, actually. So the answer is no. So for each of these databases, Cassandra, Redis, or PostgreSQL, you have to start thinking in two layers: the API layer and the storage and replication layer. So the storage and replication layer for Yugabyte is unique, built ground up from the transactional document, key to document store that I talked about. Whereas the API layer is something that we have re-implemented essentially because we like the semantics of those APIs. So we are not we don't ship with Apache Cassandra. We support the Cassandra query language. Again, this is, I would argue, this is a modern way of building database infrastructure. Cosmos DB is a great example where they have multiple different API implementations running on top of their own storage and replication architecture.
Great. Here's another great question. If you have transactional workloads running on Oracle, cache workloads running on Redis, analytics workloads which are like OLAP, Hadoop, or Cassandra, and Spark ML. For all of these, can I use Yugabyte as one source instead of multiple databases and vendors?
Yeah, great question. So the short answer is yes. Let me add a little bit color to that. Transactions and cache workloads are absolutely, because of the nature of the architecture, and because of our support for the Cassandra query language, we are actually very well integrated into the Spark ecosystem. So the same Spark Cassandra connector that's available, you can plug it against Yugabyte, and you can run aggregations, and you can on top of sort of fast moving data that is there in the database without having a separate offline ETL process, so that and then keep the aggregations or the model results back inside Yugabyte for serving purposes like user personalization, recommendations, and so on. We're not built for having OLAP workloads where the characteristics of the queries are not known beforehand, right? When you use one of our APIs with Cassandra, Redis, or PostgreSQL, you sort of need to know what kind of queries you want to perform and what kind of your data model looks like, as opposed to the OLAP world, which is primarily ad hoc and I would argue, sort of doing offline analytics over even much larger amounts of data than what you need to store in an operational database.
Great. Okay. Another question. When you talked about a whole bunch of deployments, global deployments, when would you use the option 1 versus option 2 of the global deployments?
Yeah, that's a great question. So the option 1 was essentially when you actually have a single cloud provider giving you all that you need around multi-AZ availability zones, right? But I'll give you a concrete example where that is not true because of GDPR and Brexit coming together as like a perfect storm. Customers in Europe are facing this challenge that they cannot use AWS's London region as to store EU related data, right? And unfortunately, AWS Frankfurt doesn't have enough AZs to provide strong availability. So that EU customer who has to satisfy GDPR now is more or less has no choice but to actually look towards other cloud providers to augment their AWS Frankfurt availability zones, including Google Cloud or even on-premises infrastructure, so that you can actually run a single cluster, partly in Amazon, partly in Google, and partly on-prem.
Great. Here's another one. What about real-time analytics on Yugabyte?
Oh, perfect. Real-time analytics is an awesome use case. We see that happening all the time, especially in the SMAC stack world that I talked about. In fact, one of our early customers uses location tracking information from various different places with IoT sensors coming in, and then doing real-time analytics using Spark, and then storing the result back in that, because the entire application is geared towards serving that aggregate information from that IoT data fast back to the user.
Wonderful. What is the current state of Yugabyte DB? What can I do with it now?
Yeah. So currently we're in the 0.9 beta release. We started our journey in private beta in April of 2017, and then public beta in November of 2017, and we're almost very close to releasing our 1.0 version, which is production ready, has all the critical aspects that you need to run mission critical databases, for example, backups, read replicas, and so on, so that and by the way, the PostgreSQL API inside this 1.0 release will remain in beta for some time as we continue to work with the customers and add all the remaining aspects, features and hardening and so on. But 1.0 is out hopefully next week. Please download it, use it. It'll be out there in open source.
Going to take 2 more questions. Feel free to send them in, folks. Okay. So is Yugabyte recommended for multi-region setup, or does it work well in a single region as well?
Oh, great question. Actually, the answer is both, right? In a single region setup, your needs are, I would argue, much more around essentially tolerating AZ failures, handling lots of data with high density, with fewer nodes, and those are the things that we're built for. Now what you want to do is when your business sort of demands you to go multi-region, bring your data closer to users, you want to have a database that is ready to do that, and you don't want to at that time go and find a new distribution layer like we have seen around starting with SQL, then using NoSQL to do data distribution. We are good for taking you through that journey from single region and multi-region ourselves.
Great, wonderful. Okay, so final question. If I have a Redis app, can I run it on Yugabyte as is without needing a separate database?
Oh, perfect. Absolutely. So our flavor of Redis, which is called Yedis, is actually turns the Redis API into a distributed, fault-tolerant database in its own right, so that you're not, and it is auto-sharded and all this goodness is built in, so that you can just write to Redis as if thinking that you're writing to a single database, and it will automatically handle the distribution of data across multiple nodes, the high availability that is needed when one instance goes out, and also give you all the read and write throughput that you need just by adding nodes.
That's all we have.
Okay, folks. Thank you for joining our online talk. We'll be sharing the slides and the video of this presentation pretty soon. If you want to have a chat with us, reach out to us on Gitter, on Twitter, and look forward to hearing from you. Thank you.